imagine that you're a primate in a post-impressionist forest, feasting on the fruits of your foraging here, and you notice this flash of orange in the undergrowth. Now, it might be that this is another fruit, and you can go collect it and eat some more or store it for later. But these particular forests are also known to harbor exotic beasts, sometimes orange. And so you need to decide whether to go look for it or whether it's better to run away. And of course, there are a number of cues that can feed into making that sort of decision. You can look carefully at the image. The image will have some textual information that might distinguish the peel of a fruit from the fur of a tiger. It may have some motion information that's useful. You might be able to integrate other modalities, other sensory modalities. There may be acoustic cues or olfactory cues that are useful. And you can also use contextual information. You might know something about whether fruit or foes are more likely to be found at this time of year, at this time of day, at this part of the forest. And in making a decision, certainly, and arguably there's some evidence even in the process of perception, you might integrate some information about the relative costs of the possible outcomes. Certainly in making a decision, if you're well supplied with fruit at the moment, then maybe running away is the right thing to do. But if you're hungry, if you haven't had any food for a while, then you might be willing to take a greater risk. Now, I think one of the remarkable things about brains, natural intelligent systems, about primates, ourselves, and other animals, is that we can do all of this very flexibly. We can integrate all these different sources of information. I'll quickly show you some experimental evidence, or describe some experimental evidence in a few slides, that allows you to take into account all of these pieces of contextual information, integrate them, and make what look like relatively optimal decisions. And this happens in this kind of decision-making setting where I think it's easy to think about the sources of these cues, but it's actually very fundamental to the way we experience the world. It's very deep in the process of perception, as this illustration created by Ted Adelson at MIT some years ago, I think, helps to illustrate. If you've not seen this before, if you look at the two squares A and B, most people will say that the square labeled A is darker than the square labeled B. But in fact, if you just think about the physical luminance of those two squares, the photons per unit area that are coming off the screen that you're viewing this on, they're the same. But what's happening, or one way of thinking about what's happening, is that when I ask the question or pose the question, which one of these is darker, the way you interpret that perceptually isn't as a question about the physics of the number of photons that are arriving from the screen, but as an inference about the reflectance of the surface that's being depicted. And that process of inference, just like the decision that the primate needs to make, combines local and global cues, in this case, the luminance signals, some surround contrast, the pattern, the fact that we're looking at a checkerboard, and the fact that there's a shadow being cast onto one of these things by this cylinder up here. And so the question that I and a number of other people have tried to go after for a number of years is what sorts of neural processes are able to drive this kind of flexible and apparently effortless, there doesn't seem to be a process of a slow process of inference, cognitive inference or explicit inference that we need to carry out. We just see the reflectance A and B. Okay, so one possibility, of course, is that this is just a really complicated set of functions that need to be approximated. And we know a lot about function approximation, and we know that we can, these days, using methods that perhaps are relatively old, but have become more powerful courtesy of more powerful computers and a little bit more thinking about optimization, to approximate functions very effectively. And indeed, there's evidence, as sort of is hinted at by this figure I've taken from Dan Yeomans and Jim Takala's work, that the sort of underlying architectures that we use for this kind of function approximation do resemble things that we can find in neural systems. So here we're just thinking about a recurrent neural network, in this case trained on image classification, but we might think about using, convolutional neural network in this case, we'll come to recurrent ones later. we can think about all kinds of different function approximators that could be used to try to do the sort of inference that I've just described. But there are challenges, right? Some of the challenges are common to thinking about these sorts of function approximation architectures in general from a neural point of view. They usually depend on explicit supervision for each of the functions that need to be learned. They involve what seems to be unrealistic end-to-end learning of all of the weights against a single cost function. So there's kind of a global cost that needs to be optimized. And naively, at least, in the point of view of scene understanding, we would need to have an exponentially large set of mappings in order to actually be able to learn all the different kinds of interpretation or inference that we might need to make in that checkerboard scene, right? So the thing that cast the shadow was a cylinder in that particular picture, but it could have been anything else. And the inference that I need to make about the luminance of the square or the reflectance of the square is influenced by the fact that there's a shadow there, but it really doesn't matter what it is that's casting the shadow. But if I just think about this as function approximation from an image, then each image is a different set of pixels, and they might be extremely different, right? The thing that's casting the shadow might look nothing like that green cylinder, and yet I need to interpret it in essentially the same way. Okay. And so the idea, sort of hinted at by this notion that there's a common structure here of things casting shadows, is that if we can actually extract that common structure in some way, and we have sort of inductive priors or structural priors that favor it, then this may help us to simplify the space that we're trying to search through. And of course, there's a long tradition of trying to do this in the context of machine learning as well, but it comes from a slightly different tradition of perhaps similar vintage to much of the neural network literature from the 80s. And that's the idea of using graphical models, where we actually introduce nodes that represent what we might think of as causally separable components of the environment, so edges or parts of objects or illumination, as in the case of the shadow. And then we have connections between them, and the connections reflect the direct influence between these different causal elements in the environment. And so now, because we have this limited set of edges saying what actually influences what directly, proximally, all the indirect influences, so the fact that it's just the shadow that matters, the details of what's casting the shadow matter much less, that sort of indirect stuff is collapsed through the neighbors. We just need a single node about illumination, and what it is that's affecting the illumination is kind of worked away into what turns out to be a message or a local calculation that depends on the signal that comes from the object. Okay, so the advantage to this kind of graphical structure is that it allows us to do things locally. It allows us to do both inferential processing and learning, in fact, locally, integrating out the stuff that's really unimportant. Okay, now those of you familiar with this will also know that when we usually talk about these sorts of graphical models, there's a word probabilistic that appears as well. They're probabilistic graphical models. And that's because in sort of realistic settings where we have partial information, there's a lot of uncertainty, maybe prior information that we want to incorporate. There's complexity that we might try to summarize in a Bayesian way by distributions, things that we're representing things about which we have partial information distributionally. And indeed, there may be stochasticity in the environment that we need to capture explicitly, right? All of these things drive us to use a sort of internal semantics of beliefs when we talk about the values of each of these nodes. We don't know their precise value, but we have a belief over a range of possible values. And those have probabilistic semantics, right? And this is what it means to think about Bayesian probability. We express probability distributions over quantities that we don't know, even if we don't think that they're genuinely random in the sort of frequentist sense. Okay. So it's this kind of graphical model structure that we're going to try to pursue in this talk. But before I go there, I just want to sort of very briefly take a very quick tour about forms of uncertainty that we think we know, or ways in which we know that people do process uncertainty, are able to do the kind of underlying Bayesian reasoning that we would want to implement in one of these graphical models effectively. And so I don't have time to describe these in enormous detail, so I'm just going to sort of flash them up. Those of you who know them will be reminded. Those of you who don't, at least there'll be some references that you can try to pursue. So one thing we might consider is the integration of different sources of information. So putting together the textual information and the motion information for the primate, trying to decide upon whether to go after that piece of fruit or not, or whether it is fruit or whether it is a predator. And so, this old experiment by Mark Ernst and Marty Banks looked at people's ability to integrate two sources of information about the height of a bar, haptic information and visual information, and they could titrate the reliability of these two. And again, and what they showed in this situation is that as they changed that reliability, people optimally relied on the more accurate of the two sources. So they adjusted their weighting between these two cues, but they did so in exactly the way that so the Bayesian mathematics would lead them to do. And so this suggested that integration is something that we're able to do. We're able to do it in this optimal way. A later experiment by Konrad Körding, Ulrich Bierholm, and their collaborators looked at an integration problem again. This is integration of the sound and a flash of light. And the idea is, do they, if they came from the same place, what's that place? But they also asked the question, do they in fact come from the same place, or might they have come from different places? It's depicted here in this picture, thinking about a ventriloquist dummy, which we might either think that sound and movement came from the same dummy, or we might believe, in fact, veridically, that the sound's coming from the ventriloquist and the movement is all in the dummy. And so what they found is that in reasoning between these two possibilities and trying to think about reasoning about the structure of the world, again, people and observers were able to integrate that information optimally given the uncertainty about these two different possibilities. And so again, they suggested that this sort of probabilistic Bayesian reasoning extends not just to integration of two cues or obligatory integration of two cues, but to sort of conditional integration embodied in this idea of structural inference. Louise Whiteley and I asked whether we could use, people were able to use this sort of uncertainty about something perceptual to integrate with asymmetric rewards. So now think about the primate who has to consider whether being eaten, how much worse it is to be eaten than it is to eat a piece of fruit, depending on how hungry they are. And so our very simple example of that was to ask people which of these two gratings, or rather whether the lower grating was shifted left or right, the upper one. But we gave people mildly asymmetric penalties, nothing like eating and being eaten. The payoff, if they were correct on both sides, was the same. The cost, if they were wrong, was slightly different. And so people took the safe answer, in this case the left, with slightly greater probability than the right answer. But again, we could ask whether the degree to which they do that was optimal given the uncertainty they should have based on the variability of their responses. And the answer was yes. So again, people were doing something that looked like optimal Bayesian inference in this sense. And so again, this probability extends to decisions. And then my final example is from a recent paper, Itai Leader in Mirav Ahisa's group and Vincent Adam and mine, looked at, it was a two alternative first choice task, the details of which are not important. What was interesting here was that we used different distributions of stimuli in the experiment, which are depicted in these little pictures on the left-hand side here. So there was a Gaussian distribution, or these three different colored box-like distributions. And it's long been known that when people respond in these two alternative two-interval tasks where you have to remember the first of the stimuli, the overall distribution of stimuli matters. But what we didn't know, so what was known was the range of stimuli matters. What we didn't know is whether the details of the distribution matter. And we found that they do. So people behave differently when there's this Gaussian distribution versus the case when you have say, the red uniform distribution of roughly the same range. And indeed differently again, if you have these two separate boxcar distributions in the green. And so this suggested that they could flexibly acquire prior information about the distribution of stimuli. And so another piece of the puzzle. Okay, so this sort of we see signs of Bayesian processing underlying flexibility in our ability to integrate sources of information, make inferences about structure, make decisions under asymmetric costs, and acquire priors. And again, the question is, how is this done? And all of this, one way to ask that question is, if we can process uncertainty well, how is it represented? And how does that representation subserve computation? So we're used to this idea of representation in neural systems in many contexts, right? And we think of coding, neural coding as one of the kind of the buzzwords that we've all grown up with. And sort of a canonical example might be this one. We've got a Gabor stimulus or something that carries orientation information. And we might think about a representation, I'll show you one in a moment, of that, say, in the primary visual cortex. And so somehow there's a representation of the orientation of this Gabor extracted from the image. Now, usually we start from that, and I will do that as well in a moment, and then ask, well, how do we bolt on uncertainty? Okay. Now, although I'm going to follow that same path for a moment, I want you to kind of think about the fact that, in the context that we've just introduced, the inferences that we're making, even about something as simple as orientation, are always going to be based on complex, noisy, and to a large degree, incomplete sensory data. It's very rare that we have enough sensory evidence to be completely certain about a state of the world. And so really the underlying belief that we should be looking at, just as in the machine learning case of the graphical model, is always going to be fundamentally distributional. So probably our question should be, how do we think about this sort of distributional belief representation or coding first? And then maybe as a special case, what happens when the evidence is overwhelming and there's really only one value to represent? So this notion of looking for codes or mappings between neural activity and single configurations of physical variables feels a little unnatural when you think about things from the point of view of inferential systems. Okay, and ultimately, of course, if we think of these systems and the representations as being driven by the need to behave adaptively in the end, run away from the potential foe or eat the fruit, then again, doing that well and promoting one's survival ultimately depends on being able to process this distributional information. We'll come back to spotting flies in a moment. Okay, so this is a problem that people have thought about for a while. There are a number of proposals out there. I can count sort of 4 main classes of ways in which this might be done. I'm not going to try to review them here. I think a lot of the work, though, has tended to have limited links to thinking about how these representations can be used both for learning, so how they can be learned, and how they can be used for computation, to actually do the sorts of things we want to do with these representations. And that's what I'd like to sort of try to think about in a somewhat connected way for the rest of this talk. So the one I'm going to focus on, one of these proposals, is really a very simple mechanism. And it's a particular form of averaging. But it turns out that averaging in this context can be very powerful. But let me first just give you a little intuition for what might be going on based on a simple idea of again, expanding from a standard tuning curve representation or population coding representation that we're all familiar with, even though I'm going to try to move away from that in the next few slides. So let's say we have some latent variable. I've called it Z. It could be orientation, for example, in the previous picture. And we have a neuron, and the neuron has a tuning curve with respect to that variable, right? So its firing rate as a function of the variable has maybe this bell-shaped representation. I can take a particular value of that latent variable and work out what the firing rate of my neuron would be. And I can draw that on another axis down here. So this one is an axis representing the latent variable that's being encoded, the orientation. This one is an axis of neurons. But I'm going to place the firing rate of the neuron at a location that corresponds to its optimal rate, so its preferred orientation, if you like, over here. Right? And we're somewhat used to doing this to represent population codes. If I now think about a whole population of these things, right, and again, we've got a single input latent variable sitting here, then I can plot, this neuron will have this firing rate drawn there. This neuron whose preferred orientation is up here, so is drawn at this location, has this firing rate, right? And so on, right? So I get a bell-shaped representation in neuronal population space. And this is rather sparse in terms of the number of neurons, but they could be much more densely packed. So that bell-shaped representation was more obvious. Okay, so that's the population coding as we're all used to thinking about it. What happens if instead of wanting to represent one orientation, I want to represent a belief, a complicated belief about possible orientations? Well, in a sense, I can use pretty much the same scheme, right? And again, let's look at this intuitively. Suppose that instead of just looking up the firing rate from the tuning curve, right, by just evaluating this tuning curve function psi, I instead take its expectation under the belief that I want to represent. Okay, so I'm not going to say for the moment where the tuning curves comes from or how we compute the expectation. That's going to come later. But just imagine that this is our representation for the moment. Okay, I can then do the same thing. I can calculate the corresponding expectation to get a firing rate for all of my neurons, place those firing rates in a location on this neuron index that corresponds to their preferred tuning. And now I get this distribution that sits over here. And you can see intuitively that this distribution looks like it's capturing, the pattern of firing rates captures something about the underlying distribution that I want to encode. Now we can formalize this idea. Sorry, and I should say that this sort of encoding is something that we've come recently to call a distributed distributional code. Distributed because it's distributed across many neurons. Distributional because it's a representation of distributions. Okay, it sort of goes back to, from this encoding point of view, a paper by Rich Semmel, Peter Dairn, and Alex Pouget from '98. But then in the representation I'm going to talk about, or the interpretation I'm going to talk about in a moment, was one that I and Peter had introduced in a slightly later paper. Okay, so what was that point of view? So the idea is that we can move away from this simple one-dimensional tuning curve kind of viewpoint and think about this expectations of functions in a more abstract way. So suppose I now want to encode this slightly more complicated two-dimensional distribution, but again, I'm only restricted to two because I can only draw two on the slide. This could be in general an n-dimensional distribution. The encoding functions need to be nonlinear for this to work, but otherwise they're relatively arbitrary. Okay, that's quite general. So in particular, for example, I might choose to use these threshold linear functions. So I just project onto some direction w. In this case, that direction is something like that. And then I take a half-wave rectifier. So it's 0 in this region down here, and then linearly ramps up in this region over here. Okay, so that's one of these functions. If I compute the expectation of this function under the distribution in question, I compute, and this is one of them labeled by I get the firing rate of one of my encoding neurons, Ri. And I can think of that firing rate as creating a constraint on the underlying distribution. It says the expectation of this distribution, of this function with respect to this distribution, must be the number that I'm given it, approximately perhaps, because I might have some noise in the firing. And you can think of that as a sort of generalized moment, right? A moment is the expectation of a polynomial, a homogeneous polynomial. In this case, we're thinking about expectations of other nonlinear functions. And I can now ask, well, given these constraints, what is the distribution that has the maximum, that's otherwise maximally uncertain, that is, has maximum entropy and satisfies the constraints in question? And that's a standard question. It has a standard answer. That distribution always has this exponential form where the functions whose expectations I have appear in the exponent, multiplied by these coefficients eta. The eta are actually the Lagrange multipliers in the optimization problem. But in general, they depend on the firing rate or the constraint values, but in a complicated way. Okay, but we can still work it out mathematically, and that's what I've done in this particular picture for about 20 of these threshold linear basis functions, and you can see that we actually get a fairly good depiction of the distribution that we wanted to encode. Okay, so these sorts of distributions are things that are actually very well studied in statistics and probability. They're called exponential family distributions. We're going to come back to them in some detail later on. And exponential families, in the general case, are described equally well by these coefficients eta that appear here, which are called the natural parameters, or by these constraint values R, which are called the mean parameters or the expectation parameters. And later on, we'll see that I'll use the term or the symbol mu for them as well, since they're means. Okay. But it's important to note they're not means of the variable z that we're encoding. That would just be one n-dimensional point, right? These are means of functions, and the means of the functions carry the information about the distribution in the same way as moments. Okay, so why is this? So this allows us to these means allow us to represent things. Why are they a useful representation for computation and learning? Well, the answer is that many of the things we want to do with distributions involve essentially taking calculating expected values of some sort. So if I want to make that decision, do I run or do I go find, look at what it is I saw in the undergrowth? I want to base that decision on the expected payoff of doing those two things, right? With some utility function for how much I value food versus becoming food. If I want to do this propagation of inference, I want to work out how likely it is that the reflectance of that square has a particular value given the surrounding context. In essence, what I'm doing is computing the expectation of a conditional likelihood of that variable given other variables for which I have evidence. Okay, and we'll actually write this out mathematically in a moment. Okay, but again, there's an expectation in here, and that expectation is, as we're going to see, easy to do if we're given expectations of a rich set of functions. And then finally, for learning, in particular, a flavor of learning known as variational learning, which some of you may know as the EM algorithm. What we need are expected values of sufficient statistics in order to drive that learning. So again, expectations of something. Okay, so why are expectations of these encoding functions useful to calculate expectations of these cost functions or conditional distributions and so forth? Well, the answer is that we can treat, if we have a rich enough family of encoding functions, we can treat them as a basis set in which to expand the target function whose expectation we need to compute. And if we can write that as this linear expansion, then of course the expectation of the function we want is just the same linear combination of the expectations of the basis functions, which are exactly what our code represents. Okay, so this looks sort of trivial, but it actually has a rather deep point. In order to calculate these expectations to within the approximation accuracy of my basis set representation, I don't need to ever extract the distribution in any sort of other form. I don't need to represent a density of that distribution. I don't need to represent its other moments or anything like that. I just need the expectations of my encoding functions. So this is a representation which immediately lends itself to at least these kinds of computations effectively. Okay. Let's see. Let me very quickly just describe sort of one context in which we might be able to do this sort of expectation-driven calculation, and then I'll move on to some learning. So here's a very simple problem of inference. It's just a chain inference. I have some evidence X, something I've observed. I have a pair of latent variables, one Z1 and one Z2. Think of this as maybe a local orientation, and this could be something like a global orientation, or maybe some estimate of the form of an object I'm looking at. The structure is such that this variable Z2 depends on my local image evidence only through Z1. It's the separation of dependence that the graphical model gives me that's so important for this kind of message passing. So then if I want to calculate my belief about Z2 given evidence, what I need to do is take my belief about Z1 given evidence and do this integral, right? Take the conditional distribution of Z2 given Z1 and integrate out Z1. Now, if I have a expected value representation, a DDC, of the my belief about Z1. So I have the expectations of some basis functions, which I've called psi. There are one for each of the neurons in this population. So I'm indexing those by J. Okay, and the one in the superscript tells me it's variable number one. Then, if I can create connections between this population of neurons and that population of neurons with this property, such that the connections, Aij, approximate and what this is the conditional mean of this encoding function psi on Z2 given a particular value of Z1. Okay, so this is a function of Z1 because Z2 has been integrated out. I want to express that function of Z1 in terms of the basis set of my DDC on Z1 using some coefficients. Right, these are like the alphas in my previous in the previous slide. And if those, and I can think of those weights, these coefficients, as being like synaptic weights, right? They take a psi j, a firing rate here, and give me a firing rate psi I. And if I do that, then if you work through the expectations here, the firing rate that I get, which is the linear combination of these firing rates, just assuming purely linear mappings right now, no nonlinearities in my neurons, is just the corresponding expectation, the thing I want. Okay, so that's an example of how message passing works in this framework. And we can do this where we combine multiple sources of information as well at the same time. I'm going to skip over that for the sake of time and come back to it if somebody's interested. Okay, so now I want to move on to learning, and I'm going to talk about, or try to talk about, if I have time, three different ways of thinking about learning. One of them is an unsupervised scheme based on what's called a Helmholtz machine, which has explicit coding functions. And I've included some results slides, which are sort of machine learning-y in their background, which I will skip. I'm just going to talk about the idea, since we're really interested in those ideas and how they might integrate into neural systems here. I'll then think about how it is that systems might learn to do structured message passing, so we don't have to build it in explicitly. Although I'll be used, and in particular are able to learn these coding functions in essence online, that we don't have to impose the coding functions a priori in our design of the system. But here I'll use supervised learning. And then I'll end with just some very brief comments on what we're working on now, which is thinking about how to actually do unsupervised learning, also with implicit representations of the coding functions. It turns out, interestingly enough, that the answer seems to rely on thinking seriously about recurrent circuitry and how a recurrent circuitry might create inferential systems in the brain. Okay, so let me introduce the Helmholtz machine for the first of these things. So this is an old idea introduced by Peter Dan, Jeff Hinton, Rich Zemmel, and Radford Neal back in '95. And the idea is that we want to learn a model that talks about the influence, how latent variables or causal variables in the environment influence each other. And we know about the structure of the model, but we don't know what the parameters are. Right? So we don't know exactly how this edge, for example, precisely what influence it carries. So we have a parametric form here. We're going to call these parameters theta that we want to learn. Okay, and what we do is as we learn this distribution, we use and learn at the same time a complementary network that we're going to call a recognition network. Okay, this is an idea that these days would be called amortized inference, and it also shows up in other architectures like the variational autoencoder, that some of you might have heard of. But this is another network whose job it is to take a sensory evidence, say an image, and make estimates of these causal variables. And it has a set of parameters, and we'll call those parameters rho. Okay. And learning in this kind of structure, this bipartite structure, proceeds in two phases. In the wake phase, we experience real images with our eyes open, if you like, and using our current estimate of the recognition network, we estimate what the causal structure is that corresponds to those real images. And we now use this joint between estimates of the representation and the actual image to train the parameter theta over here. Okay, and that's the wake phase operation. And this R here is just represents this network. And then in the sleep phase, we generate data from our current estimate of the world. If you like, we dream. And we use, again, the joint over these generated states of the world, in the unobservable states of the world up here, and observable, but in this case, just synthetically generated variable values down here. We use those joint observations to train our recognition network. right? So there's this bootstrapping process that you might imagine, and one can show, will tend, under certain conditions, to converge to an appropriate solution. We can't prove pure convergence in this particular setup for technical reasons that I won't go into. Okay, but you might expect that this bootstrapping procedure is something that could work well. Okay, so the first use of the DDC was a paper from a couple of years ago now that was a paper published by Esther Bertish and myself. You can see Esther up there in the corner. And the idea was to take this old architecture, the Helmholtz machine, but where we do the recognition model, instead of estimating, as they did in the original work, a simple representation of each one of these latent variables. So originally these were binary, and so the representation here was just a probability of the latent variable being 1, right? Because it's a binary variable, that's all you need. But that having an independent number for each one of them loses information about the correlations between them, which might be important, and indeed one can show in general are important. So instead what we did was we introduced a DDC. We set basis functions on this representation, and the basis functions were functions in the entire vector space of the whole layer. Okay, so they didn't encode distributions on each one individually, they just encoded the joint over the whole thing. And then using the message passing that I just described before, we can use this representation of Z1 to obtain an optimal representation of a higher layer. In this case, I've called it ZL for some top layer, but in fact, we can build a multi-layer hierarchy out of this. Okay, so each of these is a distributed representation of our belief about this layer, okay, about these variables. And now we use the fact that to learn the parameters theta over here, so notice these arrows have changed direction. This is now the generative model on the same variables. To learn this, what we need to do is calculate the expectation of a particular function, or the gradient of a function. And this function f is sometimes called the free energy. It's a bound on the likelihood of the model. Okay, but that's not so important here. What's important is that we need its expectation. And so if we can express the function itself as a linear combination of the encoding functions of our DEC, then given their expectations, as this network will learn, we can calculate the expectation of the gradient that we need. Okay. All right. And so that's what will happen in the wake phase. In the wake phase of this DDC Helmholtz machine, we experience images, we make inferences, we use those inferences to train the generative model. In the sleep phase, just as in the normal Helmholtz machine, we generate samples. We use those samples in two ways, though. One way is to train the recognition model. Okay, and if we're generating samples and there's a probabilistic relationship between these unobservable latent variables and the observations X, then simple delta rule learning will converge on the mean of the training signal psi automatically. Okay, and so that gives us these expectation representations. But we also learn the weights that are necessary to map the DDC encoding function psi to the corresponding distribution function, which is this gradient of this f object that we need to learn. Okay, and we can do that. We can learn both of those together, and now alternating between this wake phase and the sleep phase, this system will tend to converge. And actually, the richer representation of the posterior makes it more likely to converge to an appropriate answer. Right, as I said, I'm going to skip the machine learning results so that I can say a couple of words about a couple of other forms of learning. I think we started a little late, but hopefully I can manage to end well in time. All right, so let me now go on to the second kind of learning that I want to talk about. This is a project done with Kevin Lee, who you can see up here in the corner, and I think is also on the call. What we did here was to train in a supervised fashion a recurrent neural network to reproduce an unobserved quantity. In this case, the unobserved quantity was the two-dimensional location. Think of it as the two-dimensional location of a fly. So it's some dynamical system expressed in 2 dimensions, quite a complicated dynamical system. Think of it as a fly buzzing around. our observation of that was a projected and noisy one-dimensional measurement along a line here, because it's a line, it's a one dimension out of two. Okay, and that's our observation X. And we trained the network to take the sequence X, 1 to xt, and make an estimate of the location of the fly at time t. Okay, and of course we did that at all the times as we moved along. Right, so a standard filtering like problem, but like a Kalman filtering, for example, but expressed in a recurrent neural network. Now, to solve this kind of problem, it's optimally is necessary to propagate uncertainty about previous estimates of Z. But we didn't train the network explicitly to do this. There's no distributional learning built into this. We just trained it to produce the output estimate ZT. And then we asked whether distributional representations emerged within the network. Okay, and just to sort of show you that the distributional information that needs to be represented here is somewhat complicated. Here is, in this case, a trace of the true two-dimensional location under these dynamics, a posterior mean estimated in this case by a particle filter. So this is a kind of offline, more complicated system. And this is at various points in time, the posterior, the full posterior, not just the mean, being represented over these. And you can see that these are really quite complex posteriors. So in order to do optimal inference here, the system has to learn a scheme to represent something like this. So how does it do it? So what Kevin did was to basically look for this kind of DDC-like representation that we had posited might emerge from delta rule learning. And so he could take the known posteriors at different times from the particle filter and train and sort of try to identify a set of encoding functions which was sufficient to explain the pattern of activity across the whole network when at the times that correspond to these posteriors. And then could take some new posteriors at other times that weren't used in estimation of these size. So training and test here is not about training and testing the RNN. This is about training and testing our estimate of the coding functions. And so we could then evaluate whether this kind of expectation of encoding function picture was actually a good depiction of what the firing rates of our recurrent network actually represented. And we found that, in fact, it was, right? So this is the R squared in test on whether we can predict these firing rates or not using the full distribution. And it's sort of a box plot with, actually it's a scatter plot with all of the points and a box plot showing you the median with the colored line, the IQR, the interquartile range in the box, and I think the 95th percentiles in the two lines. So you can see that we're really concentrated. There's a bit of a tail, but the mass of the distribution is concentrated very close to 1. And to get this representation, we needed nonlinear complex functions psi. If we just use linear functions, which corresponds to just representing the mean of Z, because the expectation of a linear function is the linear function of the expectation, our ability to predict held out firing rates was poor. We also had more than just a Gaussian representation. If we just used a quadratic set of basis functions, which corresponds to the mean and variance of the distribution, again, we don't do so well. We really need, in this case, this radial basis function set, but a complicated set of functions. We also, in this model, it's the distribution that seems to be represented, as opposed to, say, just the history of recent presentations. It's not just memorizing recent values of X, or indeed recent single values of Z. It really seems to be carrying distributional information overall. Let me, again, in the sake of time, jump over that, which is comparing different network architectures, and just sort of highlight these now encoding functions that haven't been designed in. These are encoding functions that were discovered by the network in order to solve an inference problem. And, as you might imagine, will emerge from this kind of rather circular dynamical process. They sort of look a little bit like spherical harmonics, right? They're sort of like modes of sort of spatial modes in this two-dimensional space. But these are a good way of expressing distributions of relatively low frequency in that space. Okay, so finally, let me just sort of hint at what we're up to right now. And the idea, as I said, is to think about unsupervised learning schemes that are able to also learn these representations without our having to, as we did in the Helmholtz machine, say, here are your encoding functions. We really want the system to settle on those, as part of the optimization. And the idea is to go away from this rather feed-forward metaphor that we're quite used to in processing, which was true in the Helmholtz machine. It's actually true in the RNN work as well. If we unroll it in time, it's really just a feed-forward system like this, right? What we want to do is take the recurrence of the brain and think about that recurrence as actually fundamental to inference, so that a single pattern of inputs requires recurrence to settle into the explanation. So this is a different use of recurrence to recurrence over time in an RNN. Okay, so how do we do this? Well, we have to come back to this notion of exponential family and think actually fairly deeply about them. And so an exponential family is usually written this way. I've written it as a density over some variable, which I've called zeta for now. And it has this form, this exponential form in some function psi that I highlighted before. I've written in this vector notation now, so that's that sum that we had previously. There's a normalizer that I had just had a proportionality before, but the normalizer depends on the parameters. And there's actually another piece that we often ignore, which is a fixed distribution that's not parameterized, but it's some measure in the space of in this case, zeta. Okay. We usually define our exponential family by these functions, which we call the sufficient statistics, and sometimes the base measure, although often that's taken to be uniform. And then this normalizer or partition function follows by normalization, right? It's given by the integral or the log of the integral of the rest of it. Okay, this makes sense. This sort of definition makes sense precisely in situations where zeta is an observed variable, right, or a generated variable in my Helmholtz machine, or it has a known physical meaning. I know that I want to extract a representation of say orientation. Okay, then I might want to write down functions up here that make sense for orientation, like sines and cosines. Okay, but from the point of view of the evolutionary and learning system of the brain, nobody gives us that piece of physical meaning or gives us the nature of the variables. Those variables have to be discovered. And so choosing to represent them in this sense, it seems a little odd, right? It's unclear whether that's the right way to think about it. And in particular, I can reparameterize my variable zeta invertibly and have an equivalent representation of the underlying belief, the underlying quantity. Okay, so for example, let's take zeta, and I'm going to map it to a new variable z, and z will just be the output of this function psi itself. Right, so now z will be the sufficient statistic of my exponential family. We now have this sort of canonical form, which I've now written in measure notation, because in general, this doesn't have a density. Okay, so it really has to be, we have to think of it as a measure, but it still has the same exponential family piece here. That kind of non-densityness business, the fact that we're not absolutely continuous, goes and lives in the base measure over here. And we are absolutely continuous with respect to the base measure, just not with respect to the Lebesgue measure. Okay, so this is our canonical form, and now the family, there's no psi anymore, right? There's no exponential, there's no sufficient statistic over here. So the family we're describing is entirely defined by this base measure quantity, this thing chi, or equivalently by phi, because if you think about what normalization means, it tells us that that phi, the log normalizer, is the logarithm of the Laplace transform of chi, and Laplace transforms in principle at least are invertible. Or it's defined by the Legendre transform, or the conjugate dual, of phi. Okay, this is a convex function. I won't show you that it's a convex function, but it always is. And so it has a well-defined Legendre transform. And in fact, this is of what mathematicians call Legendre type. And so this function psi is equally good and defines the distribution equally well. Why did I take you through all of that? Well, if we think about a single recurrent network, like a nucleus or a column or something like that, and we simplify and write a recurrent circuit in just the projection activity, okay, then so we've got this function f that captures the local recurrent circuitry, including all the interneurons, right? So it's a rich function. Then we can map this to a function, to an abstract thing defined in parameter space, where mu is these expectation parameters, and this function psi that I've introduced before, okay, with a few assumptions that we need. And so this allows us to do inference. So this turns out to be the optimal inference algorithm for an exponential family defined by the function psi. And so now our distribution, our encoding functions, like the entire content of the distributional inference, is defined by the recurrent circuit, right? It's all in those weights. All right, I'm basically out of time, I think. So let me just jump through the rest of this. We can come back to it if people are interested in the question time. And I'm just going to sort of summarize at the end because we've run out of time. So what I've tried to argue is that these expectation-based representations, I think, are useful. They're useful in the sense that they provide representational power, for one thing. That was the first thing we saw. They're useful because they allow us to do various sorts of computation that we want to be able to do. For example, message passing. But also decision-making, where we're looking at expected payoffs, and indeed learning, as we saw in other examples. And that was the case in our unsupervised learning using the Helmholtz machine. In this case, we didn't use the belief propagation explicitly to do learning. Rather, we learned belief propagation through supervised learning and saw that this kind of representation actually emerges quite naturally. And then we're trying to put these things together so that we can learn to do inference in this unsupervised setting, but using distributions that end up being defined by these recurrent networks. And as I say, that's what we're after now. So let me just finish by thanking the group. The people in red here are the people who have contributed most directly to this. You saw highlighted work by Esther and by Kevin, and Ted, Merdad, Peter, and William are working on different aspects that I haven't had time to go into of the last piece. And let me also thank my sources of funding and you all for having listened.